Hi, this is Kevin. Welcome back. We're starting part 2 of the lecture for chapter 6 of the third edition of the Zelle Python book. And chapter 6 is about functions. If you haven't played part 1, please go do that and come back to us when you're done. Okay. So, functions that return values. All right. So, functions do useful things for the calling code. Okay. And you'll notice that the functions that we worked with so far print things. Well, that's not accidental. Okay. It turns out that one of the easiest and most tangible things you can do in a program is to print output to the console. So as we're teaching you to program, that's usually the first thing that we teach. Okay? Now, it turns out that calling functions that print things is only so good of a strategy. Okay? It's not really general. Okay? There are times when we want to print things to the console. There are times we want to print things to a different file, some kind of a file on the disk. There are times when we want to send that output out to a web page. So we might want that output to be part of a response from a program that runs in a web application server. And so it's more typical for us to create a function that we kind of pose some question, and then we get some answer back. And then the calling code, to the extent that it wants to print the answer, it prints the answer. Or it prints the answer in a disk file. Or it sends the answer back in a web page. Okay? The only reason that we showed you called functions that print things is because it's really easy to do, and it's really tangible, and it's really satisfying. So now we're going to explore what kind of things could functions do for us in a more typical way. Okay? And one of the things that we can do that we didn't show you how to do is how to return values from a function. Because again, you can think of a function, almost like a mathematical function. A mathematical function has arguments, it has inputs, and it typically has one output, right? And that's the answer. Okay, and then you do with the answer whatever you want it to do. Well, programming functions work very similarly. So passing parameters provides a mechanism for initializing the variables in the functions. The parameters act as inputs to a function. We can call a function as many times and get different results by changing its parameters. Okay? So most functions that we call are fairly deterministic, which is to say, if we call a function with the integer 3, and we get back the answer, the integer 6, then probably the next time we call it with the integer 3, we'll get the value of the integer 6 from that as well. That's not always the case, but it's pretty typical. Okay, so here's a function that returns the square of a number. So we say def square x. So is x a good variable name? Well, we're kind of doing algebra. And in doing algebra, x is a decent variable name. Okay? If we were doing something more applied than this, well then I would want a better a better name for the formal parameter. But the formal parameter, its name is x. Okay? And what are we going to do? We're going to return x times x. We're going to return the square. So when Python encounters a return statement, it exits the function and returns control to the point where the function was called. Okay? In addition, the values provided in the return statement are sent back to the caller as an expression result. Let's look at that. So assume that we've already entered the code for the function square, and we're working at the command line, and so we type in square and we pass int literal 3, and we get the answer back 9. Okay? Or we can say print square of 4, and it prints 16. Or we could say x equal 5, y equals square x, print y, and it would print 25. And then we would say print square x plus square of 3. So the square of 3 is 9, and x is equal to 5. So the square of 5 is 25, and 25 plus 9 is 34, and look what we got. We got 34. Okay? So what's really nice about the syntax for functions is that when you place these formal parameters in the parentheses, they really look, well, they work like a lot of the built-in functions. So you could just kind of interpret this as square of x. And what happens is that this expression for the function call takes on the value of the result when it returns. Okay? So you say x equal 5, square x, okay? The returned result is 25, so this expression, square of x, takes on the value of 25. That's what gets assigned to y. We print y, we get 25. So it has a really kind of elegant aspect when you use functions that return usable values. Just the syntax, the functions that you write kind of work just like the functions from the math package. Pretty cool, huh? So this feature of a language where you can add functionality by defining functions. This is referred to in computer science terms as extensibility. Okay? And so user-defined functions have the same kind of syntax and operation as the predefined ones, the ones that are built in. It's really pretty. So here's some math, okay? So we can use the square function to write a routine to calculate the distance between 2 points, okay? And how can we do this? Well, we use geometry, okay? So we take the square root of the square of the difference in the x's plus the square of the difference in the y's, and this is what equals the distance. So let's see. Do I like this function distance? I like the name. P1 and P2. That stands for point 1 and point 2. Okay, I'd really like point underscore 1 and point underscore 2, but that's okay. Dist. Well, he didn't want the variable to be named the same as the function. Okay, so what I have said at dist is a little too abbreviated for me. A lot of times when I want to distinguish one distance from another distance, I just give it the prefix my. So I would say my underscore distance or the underscore distance. Okay. I'm not very fond of using dist for distance. It's very old school, and we've got plenty of ink in the year 2018, so feel free to use it. The order of the function definitions as they appear in your overall program is not important or significant. We just have to make sure that a function is defined before the program actually tries to run it. Since our call to main does not usually happen until the very last line of the module, all of the functions will be defined before the program starts running. Okay? That's why we put the call to main last. Okay? It's a not a particularly intuitive place to put it until you understand that we don't want to be starting things before all of our parts are defined. Okay? Sometimes a function needs to return more than one value. To do this, simply list more than one expression in the return statement. Okay? So it's possible to return sum and a diff. Now, what we're really returning when we do this is a single value object that's called a tuple. A tuple is a combination of variables. It's a term that comes from kind of the relational calculus, the same relational calculus that's used in relational databases. Okay, so could you return two results? Yeah, or 3 or 5 or 9. When you return more than one, what happens is it takes this list and it combines them into a thing called a tuple. Okay? Then, on the other side, in the calling code, you do multiple assignments. How do multiple assignments work? Well, if you have a tuple generated on the right side, it gets unpacked into a series of variables on the left side of the assignment. So this would work for two things, num1 and num2. It would work for 3. It would work for 6. It would work for 8. Now, let me tell you that you don't want functions that do more than one thing. Okay? Now this, where what we're doing, we're entering two numbers and we're doing a sum diff. So we're going to give the sum and the difference. I don't like the idea that we're going to give both the sum and the difference. I'd rather see you call sum and then see you call diff and get one answer back each time. We have this important aspect of designing code that we're going to talk about. It's most of what Chapter 9 is about. how do you break up a problem into pieces that correspond to a good set of functions? Okay, and one of the things that we say when we get to chapter 9 is that we want the functions to be cohesive. We want them to be all about one thing. And we don't want one function to know a lot about what another function does. We call that coupling. Cohesiveness is good, coupling is bad. Okay? So this, I mean, in mathematics, I guess the sums and differences have a relationship that's stable enough that you could combine them without doing anything too heinous. But this idea that you would give a function two jobs, even related jobs, is a little worrisome. Okay? So I want to warn you off it a bit. But as you can see, by returning a tuple, which we're implicitly doing here when we're sending back more than one value, you can return as many values in the tuple as you want, and then of course you can unpack them with this multiple assignment expression that we've seen before. But don't get too crazy about this, okay? Because we're really going to try to talk you out of most of this when we get to chapter 9. One gotcha. All Python functions return a value whether they contain a return statement or not. Functions without a return hand back a special object denoted none. Okay? So that's a special value. Okay? None. Most computer languages have some values like this. Some have the value null. Others have the value nil. Okay? I think I've worked with one that has the value empty. Okay? So what does none mean? Well, it's an explicit object that means we didn't have anything to send back, so we sent you back this kind of signal object that says, well, the plumbing's actually working, so you're getting a result here, but it's not a meaningful one. Okay? So a common problem that people have when they write a value returning function is they forget to code the return. It's just kind of implicit in their head. They do all the work and they get to the bottom and they want to code the return, but they're in a hurry and they forget. Well, what's the sign of that? Well, the answer that comes back to the calling code is a value none. Normally, that's not a value that works in the context of the calling code. And you get some kind of exception condition that stops the program. So if you see an exception condition come back that stopped the program and it has to do with the value none, the first thing you should think of is, oh, I called a function that was supposed to return a proper value, but I never returned it. Okay? So all functions return some value. If you don't return an explicit value, it will return the value none for you. So, this is the same thing. So if your value returning functions produce strange messages, check to make sure you remember to include the return. Okay? Another thing to look at here on the return, let's just go back here. Returns in some programming languages, the value that you're returning has to be in parentheses. Not true for Python. So we just say return and then whatever we want to return. If you put extra parentheses around the value that you want to return, it won't break it, but you'll get a complaint from the PEP 8 style guide. Okay, they're extra parentheses. So yeah, parentheses around the returned value is not, as we say, Pythonic. It's not the Python way. Okay. Okay. Functions that modify parameters. Okay. So if we're passing parameters to functions, is it possible for the code in the function? Is it possible for that code to change the values of the actual parameters that we're passing? And the short answer is sometimes yes, sometimes no. Okay? And we're going to explore that a bit so you can understand the situation in which the answer is yes, and the answer is no. We're actually going to begin with the no side. Okay? So sometimes we can communicate back to the caller by making changes to the function parameters. That's a sometimes yes. Understanding when and how this is possible requires the mastery of some subtle details about how assignment works and the relationship between actual and formal parameters. So this is what I call a plumbing issue. Plumbing issues for me are the parts of programming that have to do with how are things hooked together. Particularly, how do they work kind of physically together? What can have, which parts can change which code? Usually have to do with an explanation of what's connected to what in what kind of way. Okay, so this is going to take some thoughtful work here, but very much worth it. Okay. So suppose you're writing a program that manages bank accounts. One function that we would need to do is to accumulate interest on the account. Let's look at a first cut of the function. Okay. So we have the function definition. It's called add interest. You pass it the balance and the rate. Okay. And then inside we calculate the new balance is equal to the balance times 1 plus the rate. So if the rate is 1%, it would be expressed as a decimal fraction. It would be 0.01. So the new balance would be the balance times 1.01. Okay? And we say, okay, let's just take the new answer and assign it to the formal parameter that we got the value from. Okay? Well, it turns out that this does not work. Okay? And now we're going to explore why it doesn't work. Okay? The short answer is it doesn't work because balance is an immutable object. It's probably a float. It could be an int. Okay? Floats, ints, and strings are immutable objects. So if we pass an immutable value object to a function, we can't change the value as seen in the calling code. And now we're going to see why. Okay? So the intent is to set the balance of the account to a new value that includes the interest amount. So let's write a main program to test this. Okay. So we have we call this a main program, and yet we call the code test. If I if I trust, there'll be a main in here somewhere eventually. So the code for test, we assign 1,000 to the amount, a decimal fraction to the rate, 0.05. Then we call add interest, passing the amount and the rate, and then we print amount. Okay? Now, if this worked, okay, amount would be 5% higher at the end, 5% higher than 1,000. So what's that? 1,050, 1050. But we run it. We run test, and ooh, it's only 1,000. So that doesn't work. And again, it has to do with the fact of passing actual parameters that are immutable values, that point to immutable values. So we passed 1,000, okay? That's probably an int. An int is an immutable value. And so there's no way that we can get the answer back in the same variable that we passed. So this won't work for ints, it won't work for floats, it won't work for strings. All three of them are immutable value objects. Okay? Kind of disappointing, but there are ways around it. So the first two lines of the test function created two local variables called amount and rate, which are given the initial values 1,000 and 0.05 respectively. We saw that. Control then transfers to add interest, the add interest function. The formal parameters balance and rate are assigned the values of the actual parameters amount and rate. Okay, so it's an assignment. Okay, you get a copy of the value in your called code. Okay, you get a copy. So the called code, is able to calculate a new balance, but it doesn't really. It's not really connected directly to balance. Why not? Because when you pass an int or a float or a string, you pass, you get a copy of the value. Okay? You don't get, you are not connected to the variable in the calling code. You just aren't. Okay? So what happens in add interest is that when we assign new balance to balance, we change balance, but balance was a copy. It was a copy of the variable that was used in the calling code, and so we don't affect the variable that's in the calling code. Okay, and again, how do we know? This is always going to be true when we're using immutable value objects like int and float and string. Okay? So even though rate appears in both their separate variables because of the scope rules. Now that's interesting thing to see is that the variable rate that is used in a test, which is the calling code, is not the same as the formal parameter rate that's defined in add interest. They have the same name, but the scope of their names applies to their own functions. They're local to their own functions. Okay? And again, that turns out to be beneficial because there's some words that you'd like to be able to use. They're very descriptive, and you don't want to have to worry, well, I wonder if I use rate in some other function. No, you don't have to worry. It only has to be unique within the function that you are in. Okay? The only thing that relates these two things is that we call add interest and we pass rate as an actual parameter, and that gets mapped to the rate formal parameter in add interest. And again, we're just getting a copy because it's an immutable value object. Okay, so the assignment of the parameters causes the variables balance and rate in add interest, those are the ones that were created with the formal parameters, to refer to the values of the actual parameters. So it's kind of funny. I say they get a copy of the value, but they actually point to the same value object. Okay? And you go, oh, that's promising. That's going to mean that we can send the answer back. Not true. Okay? We may be pointing to the same value object, but there's no way that we're going to be able to change the value that the calling code sees. Sounds like it might be promising, but it doesn't work. Okay, so here's how this works. Okay, the calling code's on the left, the called code's on the right. Okay, so in the calling code we have a variable amount, which is pointing to a value object of 1000, probably an int. And we have a rate, 0.05, probably a float. Okay, we're pointing to those two. Now, when we call the code, okay, when we call add interest, the way that we map these is that a balance and rate in the called code, they point to the same value objects. Oh, you go, oh, Kevin, this is really promising. This is going to work. It won't work. Okay. Executing the first line of add interest creates a new variable, new balance. Balance is then assigned the value new balance. Here's where it goes wrong. So let's just see what happens in the kind of memory objects internals. Balance now refers to the same value as new balance, but it had no effect on the amount in the test function. Okay, how does this work? Well, here's where we see it. Okay, so what happens is that, now let's go back. When we left the code before, amount was pointing to the 1000 value object, and so was balance. Oh, that was good. Now, after we execute the code in add interest, here's what happens. When we assign new balance to balance, okay, it's pointing to the same object as new balance, not the same object as amount. And so when we return to test, amount is still pointing at the 1000. Whereas, and so even though this seemed like it might be promising, again, if the actual parameters that you're passing are immutable objects, which is true for int, float, and string, you can never affect the value of the original actual parameter in the calling code. Because as soon as you change it in the called code, you're pointing to another object. And the called code is pointing to the same object that it always was. Okay? Oops, doesn't work. Okay, so execution of add interest has completed and control returns to test. the local variables, including the parameters in add interest, go away. So again, the scope, the lifespan of the variables in a called function, as soon as you return control, it gives up all of the memory locations associated with them so that they just vaporize. They're gone. So the local variables, including the parameters in add interest, go away, but amount and rate in the test function still refer to their initial values. We didn't really impact them. It might have seemed promising that we might have been able to, but it turns out that we can. So to summarize, the formal parameters of a function only receive the values of the actual parameters. The function does not have access to the variable that holds the reference to the value of the actual parameter. Python is said to pass all parameters by value. Okay? All right. So this turns out, this behavior that we have here, this turns out to be what happens when you encode, you appear to change the value of immutable objects, you get new objects. And we've already talked about that before in a previous chapter, but now we're seeing, oh, that has a real impact. Now, you might say, well, what about mutable objects? Don't we have mutable objects? And would that work? And the answer is yes. That will actually give you the opportunity to affect the value that the calling code has access to. And we're going to go into that in just a minute. Okay? So Python is said to pass all parameters by value. Okay, now what would be an alternative to that? Well, some programming languages, C++, Ada, COBOL, PL1, many more, they do allow variables themselves to be sent as parameters to a function. This mechanism is said to pass parameters by reference. Okay, that's not what Python does. Okay. If you do it by reference, when a new value is assigned to the formal parameter, the value of the variable in the calling program actually changes. Okay? That's another architecture entirely. Doesn't work that way in Python. Okay? Since Python doesn't have this capability, one alternative would be to change the add interest function so that it returns the new balance. Okay, so this is usually the way that you solve this. Okay, it's considered polite. Okay, to not be changing the values that you're passed. Okay, so by convention, according to good practice. Okay. If somebody is to pass you a parameter, an actual parameter, unless the definition of your called code, unless implicit in it is the idea that you're going to change the formal the actual parameter that you're passed, then you ought not change it, even if you could, right? So this the typical thing that you do is that you're passed in the actual parameters, and instead of changing the value of one of those actual parameters, which is pretty hard to do, as we just saw, it can't be done with immutable value objects. Well, then we just return the new balance, right? So what does it look like here? Well, we get in the balance and the rate, and then we calculate the new balance, and we return it, okay? And then we can say, something like this. We can say something like amount equals add interest, amount, and rate. So on the right side, the amount is the value before add interest has been executed, and the amount on the left side gets the value after add interest has been executed. So this is how we normally do it, okay? And it's really a polite thing to do, okay? You don't want to be mucking around with the values of the variables that people send you. This is a very safety-oriented kind of practice. Okay? Even in languages like some of the ones that they mentioned, where parameters are passed by reference, and you can easily impact the values from the called code. It's considered impolite to do that there unless it's part of your kind of mission or charter. Okay, so this just enforces it with a language feature, which is pretty safety oriented. Okay, instead of looking at a single account, let's say we're writing a program for a bank that deals with many accounts. We can store the account balances in a list and then add the accrued interest to each of the balances in the list. We could update the first balance in the list with code like, okay, so we say balance is 0, so that's an index, that's the first item on the list, equals balance is 0 times 1 plus the rate. Okay. Well, will this work? Yeah, it turns out it's going to work. Why does it work? It works because lists are mutable or changeable objects. Okay. So this code says multiply the value in the 0th position of the list by 1 plus the rate and store the result back into the 0th position of the list. A more general way to do this would be with a loop that goes through the positions 0, 1, blah, 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 blah to length minus 1. Okay? All right. So we have here a program called addInterest3. It illustrates modification of a mutable parameter, a list. Okay? So if you pass an int or a float or a string, you can't change it. Okay? You can't influence the value as seen in the calling code. If you pass a list, because lists are mutable objects, you can actually change the values of that actual parameter as seen in the calling code. Okay? Because list value objects, you're able to ask them to change their state. Okay? That's what makes them mutable. Whereas floats and ints and strings, you can't ask them to change their state. You can do things that look like they do, but what happens is they send you back a new value instead. They send you back a new value object. So you're not really changing the original value object. Not true for a list. A list is a mutable object. Okay? So here's what we do. In addInterest, we say, so we're getting a list called balances, and then we have the array. So we say for I in range length of balances. Okay, so that's going to get us, we're going to go through the balances. We say balances I equals balances I times 1 plus the rate. Okay? And now we've got test. So we have 1,000, 2,200, 800, 360. The rate is 0.05. Add interest amounts I wouldn't have said 0.05. I would have said rate. I think that's what he meant to say here. And then he says print amounts. Okay. And we're actually going to, so this is the calling code. We're actually going to see that the values in the list are going to be swapped out with higher values. Let's go look. So our original code had these values. The program returns 105% of the values. What happened? Python, it passes parameters by value, but it looks like amounts has been changed. I think it was actually balances that got changed. So let's see. Oh no, in the called code it's called amount. In the calling code it's called amounts. In the called code it's called balances. Well, that was a good thing to do to emphasize the difference. Okay, so but it looks like the values in the amounts list have been changed, and they have. So we talked through this. The value of the variable amounts is a list object that contains 4 int values. Okay, we know that. So this is how it looks. Okay, so if you look at the code that we have here from the calling code, he doesn't call with 0.05. He calls with amounts, comma, rate. Okay, so that's the right thing. So in the called code, rate, it points at a float, an immutable object, 0.05. In the called code, the same thing. We use the same name, even though it's not the same variable, and it points to that same object. That's fine. Amounts points to this list object, and balances gets mapped so that it points to the list object as well. Okay, and lists are complex objects. So this list holds the references to 4 what appear to be ints. Okay, so now we're going to go on here. So next, add interest execute. The loop goes through each index in the range of 0, 1 to length -1 and updates that value in balances. Okay. So now what happened? Well, what they've done is to show us that here are the original value objects. These are the lower amounts. Okay. Now, as soon as we replace them with the higher value objects, these, because there are no variables pointing to them, they become what we call candidates for garbage collection. So for some short time, until the Python infrastructure decides it wants to clean up the memory, maybe these are just kind of floating around with nobody pointing to them. As soon as it runs the garbage collector, zoop, they're all going to be collected up and they're going to be gone. Okay? So what's happening is the list is pointing to 4 new objects. Okay? That's because it's the list is a couple of things. One, it's a complex object. It's an object that has sub-objects. Okay? And we'll learn more about them as we go through the course. But the other thing is it's mutable. It can point to a revised set of sub-objects. So after add interest executes, okay, the list is pointing to 4 new value objects. And these things have been orphaned, soon to be garbage collected. So in the diagram, the old values are left hanging around to emphasize that the numbers in the boxes have not changed. But the new values were created and assigned in the list. The old values will be destroyed during garbage collection. Makes sense. So when add interest terminates, the list stored in amounts now contains the new values. The variable amounts wasn't changed. It's still a list, but the state of the list has changed, and the change is visible to the calling program. Okay? Parameters are always passed by value. However, if the value of the variable is a mutable object, like a list, then the changes to the state of the object will be visible to the calling program. This is another case of aliasing, which they talked about in Chapter 4, but we did not cover. I just, before we get off of this, okay, I just want to say that whatever function you have, okay, it should be pretty clear that it only changes the value of some object that it has been passed if that's within the charter of that function. Okay? Admittedly, this add interest could have a charter that says, well, we ask the values, we ask the list to change the values, and we do. We tell it to change the values that are held in the list. So that's really part of the charter. If in fact we do it in some kind of a sneaky way, okay, if somebody says, let's say you have a function called it says something like this: to calculate the sum of list items. So you want to add them up, right? Well, you better not be changing their values inside of that, even though it's possible to do, because we've seen that in the called code, we can change the values that are in the list. It's not a polite and responsible thing to do. So you should only be doing that if it's the nature of your charter, your mission, to change the values in that changeable object. Okay? Because if not, it's an impolite and improper thing to do. Enough said. So far, functions have been used as a mechanism for reducing code duplication. Another reason to use functions is to make your program more modular. As the algorithms you design get increasingly complex, it gets more and more difficult to make sense out of the programs. One way to deal with the complexity is to break an algorithm down into smaller subprograms, each of which makes sense on its own. And that's a kind of a refactoring that we do, where we typically we don't want functions to be that big. 10 lines is fine. 20 lines is probably okay. 100 lines is probably too big. Okay? So the longer the code in the function gets, the more suspicion that we have that it's about more than one thing in a way that's hard to understand. And what we're going to learn how to do when we get to Chapter 9 is to use refactoring to pull subparts out into functions that are properly named, such that we get a much more readable and maintainable program. Okay? And that's a particular kind of refactoring that's really valuable. So we're not going to overload you by having you do that in Chapter 6. We're going to wait till Chapter 9. It's a fun thing to do, and I'm looking forward to it, but we're not going to do it quite yet. So I guess here's the last couple of slides are some kind of a refactoring that's been done with the graphics program that they had, which of course we didn't actually cover this, so we're not going to cover that. So I'm going to promise that we'll do that kind of refactoring of programs that get too big before refactoring. We'll do that in Chapter 9, and as I said, we'll have some fun. So that's it for Chapter 6. I'll see you again next time. Bye-bye.